All right, so in this module, we're going to go ahead and look at the sp2 type of hybridization. So again, this is going to be carbon. So we saw the ground state for carbon. We had 2 electrons, in the, so 2s2, and we had 2 electrons and 2p2. And so this is how that would look. So how we can visualize the sp2, and again, from the name, you might be able to recognize that we're going to take 1s and 2p, and that's going to be the hybridization. So how we can kind of visualize this is, first, if we consider that an electron from a 2s is actually excited, so we create this kind of intermediate excited state. And then what we're going to do is effectively form the hybridized state, where we hybridize 2 of these with 1 of this. And so we get 3 at the intermediate, right? So this sp2 is intermediate of the 2p and the 2s. But in doing that, you'll notice that we leave behind a p orbital. So this is an unhybridized p orbital. And again, the important thing here is that we've basically kind of merged the 2s, so there's no longer 2s down here, but we have a 2p sp2, and all of those are half filled, and same thing with unhybridized p orbital. So this is kind of how you can think about the formation of the sp2. So we leave behind 1 p orbital unperturbed. And everything is, again, half filled, so each one of those is going to want to bond with an adjacent atom that has a similar hybridized structure. So you have to always think about it. You can think of it as isolation, but obviously it's going to be bonded to something else. So the sp2 orbitals, these are the sigma bonds, and then the p orbital that remains is actually going to be that weaker pi bond, and we'll see those in the next slides. Okay, so let's look at like the result of this sp2 hybridization. So in carbon, this forms what is known as the graphite structure, and because we're dealing with 3 orbitals, we deal with 3 lobes, and in this case they're in plane, and they're 120 degrees apart. And if you kind of think of this as 1 carbon with the orbitals, then what you can do is you can kind of extend that as if those start to bond together. These are all in plane, so we get a planar structure that's very honeycomb in nature, right? This is the basically hexagonal honeycomb structure of graphite. And so the in plane are these sp2 orbitals that hybridized, and so those are the strong sigma bonds. And then that leftover p, we haven't forgotten about that. Those leftover p orbitals are actually the bonds between the planes. So you're not really seeing them here, but what's holding these planes together is those p orbital, or those pi orbitals, sorry, which are the remaining p orbitals, and those are weaker in these cases. So let's again kind of look at the energy diagram from carbon. So here it's on the left side, same structure. When we hybridize, we leave 1 p behind and we form sp2, each one of those half filled along with this. And again, we're going to kind of ignore the 1s because it's full. And when we bond carbon to other carbons in this honeycomb structure, what happens is the sp2 forms a sigma bond here, and then an anti-sigma, the sigma star. So this is the bonding, this is the anti-bonding. This is completely full, this is completely empty. But we also form pi bonds with the p orbitals that are left. So we have these, since it's, so here it's forming with, you can see that in that structure, right? Or if you look over here, one of these carbon is going to have to bond with 3 others in this chain. And so that's how we kind of get the numbers that you're seeing here with the pi bonds. And so in that case, those 4 total carbons each contribute 1 electron. And so in this case, you have partially filling of this pi bond. All right, so those in between bonds, these pi bonds from the leftover p orbitals, form van der Waals forces. So those weaker bonds between the hexagonal layers of graphite. And so this is actually how, if you've heard of graphene, that's how graphene was created. So basically, they took a piece of pure graphite. So what you see here, this is pure graphite. And then if you basically put a piece of Scotch tape on it and peel it back, you peel off one of these layers, or multiple layers, and you break the pi bonds. And then you just have this two-dimensional structure. You just have this one layer of carbon. So you've isolated a single sheet of graphite, and that's what's known as graphene. And it has very interesting properties because it's just two-dimensional structure. And so that gives it some interesting properties. So let's look at graphite. So again, graphite, we talked about those pi bonds. Because those pi orbitals are partially filled, like you see here, that gives us electrons for conduction. And so that's where the electrical conductivity of graphite comes from, is those pi bonds that are pi orbitals, sorry, that are partially filled. All right, so we've talked about sp3 in the previous module and sp2 in this. So sp2, sp3, but there's also a lot of other types. There's ones involving d orbitals, but sp2 and sp3 are the most common, so that's why we talked about them. And we won't really talk about these others that are out there, but I want you to keep in mind that there are other types of hybridization that involve different combinations of sp and even d orbitals.